So I come from École Polytechnique Fédérale de Lausanne in Switzerland. Today I'm going to talk about quantum and nonlinear plasmonics. Well, here is an outline of my today's talk. So from the previous speaker, we heard about glowing plasma, and I will talk about plasmons, which seems to be related, but indeed they are related, but slightly different. So first, let me try to put everyone on the same page and make a brief introduction to the field of plasmonics and explain what's that. So by definition, surface plasmons are collective oscillations of conduction electrons at metal dielectric interfaces. And you may ask, what does it have to do with plasma? The answer is quite simple. The thing is that at optical frequencies, metals do behave essentially like plasma, because there are a lot of free or quasi-free electrons in metals, especially in noble metals. And if the electric field drives the oscillations of these electrons is fast enough, then they essentially behave like plasma. So in these surface plasmons, they appear in many different types. One of the most commonly known is so-called localized surface plasmon. So here is the illustration of this principle. So say we have a metallic nanoparticle, and the size of this metallic nanoparticle is comparable or less than the wavelengths. Then the electric field that drives the oscillations, the free electron oscillations in this metal nanoparticle will make them oscillate with the field. And for certain conditions that depend on the material properties of this nanoparticle and on the size, geometric size of this nanoparticle, we may get what's known as localized surface plasmon resonance. So here is shown as a peak in this scattering cross-section. On the other hand, there is another type of surface plasmon, which is known as SPP, surface plasmon polariton, also traveling surface waves. So if you have a metal dielectric interface, then and solve the Maxwell's equations, you'll find that there are modes that exist at this surface. However, they are not so easy to excite because you need special coupling mechanisms. So as you can see from this plot, the blue and orange lines are the dispersion relations, dispersion curves for the SPPs at gold air and gold glass interfaces respectively, but they are both located below the black dashed lines. These black dashed lines are basically the light dispersion. They're just linear dispersion of light in free space. So these modes are not easy to excite. That's what makes them special. And now let me discuss in more details these localized surface plasmon resonances from the perspective of energy, electromagnetic energy balance. So if we first consider conventional photonic cavities, like say mirrors that we are all familiar with, hopefully, then the point is that the electric energy, electric field that's shown with blue color here, and magnetic energy, the magnetic field, sorry, and it's shown with red line here, they are in balance. So basically, oscillation of the electric field induces oscillation of the magnetic field, and self-sustained oscillations are possible in such a system. However, if we make this photonic cavity smaller than the wavelengths of the light, these self-sustained oscillations are no longer possible because the electric and magnetic energy are not in balance anymore. However, if we take a plasmonic cavity in this nanoparticle, where part of this energy can be stored in a form of kinetic energy of electrons, this energy balance can be restored, and self-sustained oscillations are possible. However, the problem is that this system is very lossy. There is strong damping related basically to ohmic losses in the metal. And this is actually a huge problem in plasmonic frequency. So this topic became popular in the late 90s with the advancement of nanomaterials and nanotechnology. At first, people were very optimistic about it. But then step by step, they realized that losses are a severe problem. And there was this anger step in the development of the plasmonics field. But then slowly people realized that actually sometimes these losses are useful and we can make use of these losses. So this led to a number of appealing applications in plasmonics, well, say in sensing, photochemistry, structural colors, so-called metasurfaces, which is also a hype field now. Even in solar energy harvesting, we are often now using these plasmonic nanoparticles to enhance absorption. Interestingly, I bet that everyone in this room has had encounter with plasmons in recent years. If you have done the COVID test, rapid antigen COVID test. So of course the sensing mechanism has nothing to do with plasmonics, but the reason why we see this 1 or 2 stripes in a test is because these tests, the tests include gold nanoparticles. So the reason for the red color is plasmon resonance. Although the biological properties of these nanoparticles, which I have no idea about, are responsible for basically detecting the COVID antigens. This was sort of a theoretical introduction and a brief overview of possible application, but now let me switch to experimental part. So traditionally for plasmonic devices, we use so-called physical vapor deposited noble metal films. A big problem here is that these metal films are very rough. You cannot create like perfect film just by sputtering or evaporating metals on the surface. And recently, people came up with a number of alternatives. One of them is this monocrystalline gold flakes. So basically, very thin gold crystals, chemically synthesized, that have high aspect ratio and very smooth surfaces. And they are perfectly crystalline, as the experiments show. And this perfect crystalline structure allows to significantly reduce the losses that are related to scattering on these crystal grain boundaries in traditional thin films. So, and this gold flakes was a part of my PhD research that I did during my PhD studies in Denmark. And here is just a quick side note that these monocrystalline gold flakes are funny beasts themselves. So here you can see that depending on the illumination conditions and the observation conditions, basically numerical aperture of the objective lens that you use in your microscope, the side walls, the edges of these crystals appear with different colors. And this is due to excitation of localized surface plasmon resonances. And the colors, the exact colors, are defined by the thickness of the gold crystal and, as I mentioned, illumination conditions. So actually, the title of my talk was quantum and nonlinear plasmonics. So now let me come closer to the quantum part of it. The interesting point is that all what I talked about previously can be described using classical electrodynamics. There is nothing quantum in usual plasmonics, although term plasmon suggests that it is quantum. No, in fact, it's just historical heritage. It's classical electromagnetic wave that occurs at metal dielectric interface. However, if you make your metal layer very, very thin, say you reduce the thickness D down to a few atomic layers, then you start to observe quantum confinement effects. So in this case, in the work of my colleague, Alvaro Echari, they performed DFT calculations to show that if you reduce the thickness of the gold layer down to 5 atoms, you start to see discretization of the band structure. Because, as we've seen in one of the previous presentations, typical bulk crystals of metals are basically have continuous bands. But here we start to see discretization. And the problem, also as mentioned by the previous speaker, is that these DFT calculations are very, very costly in terms of computing power. So people were trying to come up with the semi-classical or semi-quantum, if you wish, methods for calculating this mesoscopic quantum confinement effects. So, and one of them is known as Feibelman Z parameters, which basically modifies the boundary conditions for the fully classical description to take into account quantum effects such as Landau damping that occurs in these mesoscopic structures. And this way the calculation becomes much faster, but this quantum effects can be revealed. And now let me shift the gears a little bit again and introduce you to another type of surface plasmon, which is known as gap surface plasmon, which occurs at the metal dielectric metal heterostructure. And it actually has a similar dispersion diagram as compared to usual conventional surface plasmon polariton, but it allows to confine the electromagnetic radiation to much more narrower gaps, for example, down to single-digit nanometer gaps. And classically, as known from basically 60s, the dispersion relation is described by this equation, which is actually not possible to solve analytically because it's transcendental. But if you make this gap very small, again, you start to observe this quantum confinement effects. So it's not necessary to make the metal very thin. You can also make the gap between two metal surfaces very thin to start to observe this these quantum effects. Here they actually manifest in so-called non-local effects, but do not confuse these non-local effects with usual quantum non-local effects. By non-locality here is meant the fact that the dispersion relation is modified by this delta term, which contains the wave number of this gap surface plasmon mode itself. So basically, it becomes recursive, and this equation is even more difficult to solve. What was the point that I wanted to make? It's complex, and it involves this equation, although it looks quite simple and quite classical, it involves these quantum effects. So, and actually, yeah, the point was that we wanted to study this spatially dependent non-local effects experimentally, and for that we used scanning near-field optical microscopy. So here's a schematic picture of the setup. The idea is that we have a atomic force microscopy chip, usually a AFM chip, that is then irradiated with the laser light, in this case 1550 standard telecom laser. And by scanning the sample with this AFM chip, we can detect then the scattered light and construct this so-called near-field maps. And by use of so-called heterodyne demodulation, we can then obtain both amplitude with the red-yellow color map and phase information that is shown with the blue-white-red color map. So basically, you can see that we launch a plasmon wave that travels along this. Maybe I'll better show it on the next. Yeah, here it is. So we have our gold flake sample, and then we put another gold flake on top of it to create this cavity. And we also prepared this SPP gratings to launch, actually, to couple to these modes, because as I mentioned in the beginning, these modes are not easy to couple to. But then, yeah, this grating launches the gap surface plasmon, and we can study its propagation. And then actually we studied many samples with varying thickness of the dielectric gap, and we observed that if you go to very small gaps, say down to 2 nanometers or 3 nanometers thickness, we start to observe this deviation from the classical curve, and we need to take this non-classical effects into account. How much time do I have?
1 minute.
Okay, then I will also mention a couple of applications with these gold flakes that is related to quantum information technologies. So these two works were conducted in collaboration with my former colleagues in Denmark, where we used high quality of these gold flakes to create this V-groove type of waveguides and couple quantum emitters to this waveguide. So as shown here, we place a fluorescent molecule on the one end, and we radiate it with laser light. Then it pre-emits with at some other wavelengths, and these wavelengths can be collected at the other end of the waveguide, and it still preserves its single photon particles. And here, this work is basically similar to the previous one, but the configuration of the waveguide is slightly different. Here it's like V-groove, so we kind of made a trench in the metal. Here it was opposite. We created a dielectric structure atop of this grating, and then we used the different types of emitters to basically obtain the same goal: quantum emitter that is launching single plasmons. I also wanted to talk about nonlinear optical properties of gold, but maybe I'll skip. I just mentioned that again, gold flakes have very peculiar, unusual nonlinear optical response. If you're interested, feel free to come by after talk, and we can show you more and discuss. Yes, with this, I would like to thank Arnold for putting the conference together and giving opportunity to present. I was supposed to present tomorrow, actually, but unfortunately, there was a schedule issue. So thank you again for this opportunity. And also I'd like to thank my supervisors and all former and current colleagues that are in Denmark, in Switzerland, and also in Germany. And of course, thank you for your attention.